Hey everyone, and welcome back for another deep dive. This time we're going way back, like way back. Ancient Greece, in fact. We're tackling Euclid's Elements.
Oh, yeah, Euclid. Most people probably remember him from, high school geometry.
Right, exactly. But there's so much more to this book than just triangles and circles. Like, it's really a masterpiece of logic and deduction.
Yeah. And I think what's so cool about it is that it gives us this, incredible glimpse into how the ancient Greeks thought about math.
Totally. So we're going to be using a book by Ian Mueller as our guide for this deep dive. His book, Philosophy of Mathematics and Deductive Structure in Euclid's Elements. It's a pretty dense read, but it's full of fascinating insights.
For sure. Mueller really digs deep into, the underlying philosophy of the elements. It's not just about the math itself, but, the whole way of thinking that goes into it.
Okay, so let's get into it. One thing that really struck me is how important construction was to Euclid. Well, absolutely. I mean, for him, it wasn't enough to just describe a geometric figure. You had to actually be able to construct it, like step by step, using a limited set of tools.
Right. And Mueller points out that Euclid used only 6 basic constructions as his, building blocks.
Yeah, joining points, extending lines, cutting off equal segments.
Bisecting lines, erecting perpendiculars, and copying angles. Just those 6.
It's amazing, right? Like, everything else in the elements is built up from those 6 basic constructions.
It's kind of like those Lego sets where, you have a bunch of different bricks and you can combine them in infinite ways to build all sorts of crazy stuff.
Exactly. And you know what's even crazier? Euclid used those simple tools to prove some seriously complex theorems, like the Pythagorean theorem.
Oh, the Pythagorean theorem.
Yeah.
Like a squared plus b squared equals c squared.
That's the one.
Yeah.
Imagine trying to prove that using only those 6 basic constructions. It really shows you how powerful Euclid's methods were.
That's mind-blowing. Okay, so we've got these 6 basic constructions, and Euclid uses them to build up more and more complex ideas.
Right, and this is where we get to the idea of a deductive chain. Every proposition in the elements builds on the ones that came before it, kind of like a...
Like a chain of dominoes, right, where one falls and knocks down the next one and so on.
Perfect analogy. Or like those flow charts,
Yeah.
where each box represents a proposition and the arrows show what it depends on.
Oh, yeah, Mueller has some great diagrams of this in his book. He shows how, proposition I.45, which is about constructing parallelograms, builds on all these earlier propositions. It's really cool to see how everything fits together.
It really highlights the systematic nature of Euclid's approach. Yeah. And he wasn't just throwing out random ideas. He was building this incredibly intricate and logically sound system.
Right. So this whole deductive chain thing, this rigorous way of building up arguments, it seems pretty different from how we often think about math today.
Oh, yeah, definitely. And it leads to a really interesting question about, the relationship between Euclid's geometry and modern algebra.
I was going to ask about that because, I've heard people say that, book 2 of the elements is basically just algebra in disguise.
I've heard that too. But it's actually a bit more complicated than that.
Okay, so how so? What's the difference?
Well, modern algebra is all about abstract structures and relationships, right? We use symbols to represent quantities and manipulate them according to certain rules.
Right, like x plus y equals y plus x, that kind of thing.
Exactly. But Euclid's geometry is much more tied to, the visual representation of shapes and their properties. It's not just about the relationships, but about the actual concrete things themselves.
So it's more like we're dealing with actual lines and squares and circles, not just abstract symbols representing them.
Yeah. And Mueller makes this point that, trying to source modern algebraic ideas onto the elements can actually kind of distort our understanding of what Euclid was really doing.
So we have to be careful not to, project our own modern ways of thinking onto the past.
Precisely. We have to try to understand Euclid's work on its own terms. Try to see the world through his eyes, so to speak.
That's a great point. Okay, so we've talked about construction, deduction, and the difference between Euclid's geometry and modern algebra. What else is there?
Well, there's a whole lot more, but I think a good place to go next would be to talk about proportion and ratio.
Yeah, that's where things start to get a little bit... abstract even for Euclid, right?
Totally. And this is where Mueller's book is super helpful because he kind of guides us through Euclid's thinking on these topics. It can be tough to wrap your head around, but it's super fascinating.
Okay, so proportion and ratio, what's the deal with those?
Well, it all starts with Euclid's theory of magnitudes. These are abstract quantities like length, area, and volume.
Okay, so we're talking about, how big or small something is, but in a more general sense.
Exactly. And the way Euclid defines same ratio is like pretty different from how we think about it today. Mueller actually uses sets of fractions to explain it, which I found really helpful.
Oh, interesting. I remember that part from the book. It's almost like Euclid is like grappling with infinity in a way, even though he doesn't have the same tools we do.
That's a really good observation. It's like he's intuiting something profound about, the nature of quantity and how it relates to infinity.
Wow. Okay. I'm already feeling my brain stretching a bit here, but it's exciting. Tell me more about these magnitudes and ratios and how Euclid thought about them.
Okay, so one really crucial thing is that Euclid doesn't assume what we call trichotomy. Like, he doesn't automatically say that for any two magnitudes, one has to be greater than, equal to, or less than the other.
Right. He doesn't assume that, but that seems so obvious. Like, how could it be any other way?
I know, right? It seems like a no-brainer to us, but Euclid's approach is much more subtle. It's like he's saying, hold on, let's not just assume this, let's see what happens if we don't.
So, what does happen? Like, what are the implications of not assuming trichotomy?
Well, one big implication is that it leads to what we call the Archimedean condition.
The Archimedean condition, what's that?
It's this principle, named after Archimedes, who came after Euclid, that basically says, no matter how small a quantity you have, you can always add enough copies of it together to exceed any other quantity, no matter how large.
Okay, I think I get that. So, like, even if you have a tiny little speck of dust, you can keep adding more and more specks of dust until you have a pile bigger than Mount Everest.
Exactly. And this condition turns out to be super important for all sorts of mathematical reasoning, especially when we're dealing with infinite processes.
So, Euclid's not explicitly talking about infinity, but he's setting the stage for it with this whole idea of the Archimedean condition.
Yeah, it's like he's laying the groundwork for future mathematicians to explore the concept of infinity in a more rigorous way.
This is wild. I mean, it really makes you appreciate how deep Euclid's thinking was. He was tackling these really fundamental questions about the nature of quantity and magnitude, questions that still resonate with us today.
Absolutely. And, you know, this whole line of thinking leads to one of the most mind-blowing discoveries in ancient Greek mathematics, the concept of incommensurability.
Incommensurability. Okay, that sounds kind of intimidating. What's that all about?
Think about trying to express the square root of 2 as a simple fraction.
Like a number over another number.
Right. Turns out you can't do it. The square root of 2 is what we call an irrational number, and this discovery totally rocked the ancient Greeks' world.
Wait, so they couldn't just write it as a fraction? Like, what did they do?
Well, they called these kinds of quantities incommensurable, meaning they couldn't be measured with a common unit.
So, like, it's like you have two lengths, and no matter how small you make your measuring stick, you can never find a unit that perfectly measures both of them.
That's a great way to put it. And this discovery, totally challenged their whole understanding of numbers and geometry. It was a major paradigm shift.
Wow, so they're wrestling with these irrational numbers, and it's blowing their minds. What did Euclid do with this whole incommensurability thing?
Well, in Book X of the Elements, he actually develops a whole system for classifying different types of incommensurable magnitudes. It's super intricate and detailed, and it shows just how far he was willing to go to understand these seemingly paradoxical quantities.
Okay, so he didn't just shy away from this challenging idea. He dove right in and tried to make sense of it.
Exactly. And it's in these later books of the Elements where he's grappling with these more abstract concepts that we really see Euclid's genius shining through.
This is amazing. I'm starting to see how the Elements isn't just a geometry textbook. It's like a window into a whole different way of thinking about the world.
Oh, right. And, we've only scratched the surface here. There's so much more to explore in Euclid's work. Like, how did he deal with shapes like circles and spheres, which aren't made of straight lines?
Oh, yeah, good point. That seems like a whole other level of complexity. How did he approach those kinds of shapes?
That's where the method of exhaustion comes in, which is, well, it's pretty mind-blowing.
Okay, I'm hooked. Tell me more about this method of exhaustion. What was Euclid doing with it?
So this method of exhaustion, it does sound kind of, well, exhausting. What was Euclid actually doing with it?
Yeah, it's a bit of a brain twister, but really clever. Basically, it was Euclid's way of dealing with curved shapes. You see, he couldn't use his usual straight edge and compass constructions for those.
Right, because circles and stuff, they're all curvy, not straight lines.
Exactly. So imagine you're trying to figure out, say, the area of a circle. What Euclid would do is inscribe polygons inside that circle.
Polygons like squares and triangles, those kinds of things.
Yep, those are the ones he'd start with, say, a square nestled right inside the circle.
Okay, I can picture that. Then what?
Then he'd get a bit more complex. He'd add more sides to the polygon, maybe make it a hexagon, then an octagon, and so on. Each time, the polygon fits the circle a little more snugly. Ah, I see. So it's like he's gradually filling up the circle with these increasingly complex shapes.
That's a great way to think about it. And with each step, he could calculate the area of the polygon, getting closer and closer to the actual area of the circle.
Okay, that makes sense. But did he actually ever prove that this method gives you the exact area of a circle, or is it more like just a really good approximation?
That's a really sharp question. It highlights a key difference between Euclid's method of exhaustion and what we use today, calculus with its limits and all that.
Ah, calculus. Limits. That takes me back to some fun college classes.
Right, so Euclid's method was definitely rigorous, but it didn't have that idea of a limit, that we can get infinitely close to a value. He was more focused on proving relationships between areas, not so much about finding exact numerical answers.
So even though he couldn't nail down the exact number for, say, pi, he could still use this method to show how areas related to each other in a precise way.
You got it. He was laying the groundwork for ideas that would be developed much, much later with calculus.
Wow, that's incredible. It's like he was centuries ahead of his time in some ways. And, it really makes you appreciate how the Elements wasn't just some dusty old textbook, but a foundational work that shaped the whole trajectory of math.
Couldn't have said it better myself.
Yeah.
It really speaks to the power of, clear thinking and systematic reasoning, It's a timeless approach. What's been standing out to you the most about Euclid's work?
For me, it's how Euclid blends this real rigor with creativity. He's got this super precise way of thinking, yet he comes up with these really innovative ideas, like this method of exhaustion we're talking about, or his whole exploration of incommensurable magnitudes. Those must have seemed revolutionary back then.
Oh, absolutely.
Yeah.
I mean, imagine being a mathematician back then, thinking everything's nice and neat with whole numbers, and then bam, incommensurability hits you.
Right. Total mind-blowing stuff. And to think he did all this with just those 6 basic constructions we were talking about earlier, it's pretty remarkable.
It really is. The way he uses deduction, builds these logical chains. It's like weaving a tapestry, connecting all these ideas into this coherent whole. Just amazing.
I have to admit, when I first picked up the Elements, I thought, okay, this is going to be dry, this is going to be technical, but it's been anything but. It's like a journey into the mind of a genius.
Totally agree. It makes you wonder, what other gems are hidden away in ancient mathematical texts? What other insights are just waiting to be rediscovered, maybe even reinterpreted with our modern tools?
That's a great point. It's like maybe there are other methods or concepts from ancient times that could shed new light on today's problems, or even spark new discoveries. It just shows how history isn't just about the past. It can really inform the present and future.
Exactly. Studying math history is not just about memorizing formulas or theorems. It's about understanding the evolution of thought, how people grappled with these really fundamental questions about the nature of, well, everything, really.
I like that. It's like we're tracing the lineage of ideas, seeing how they've developed over time, and maybe, just maybe, we can contribute to that lineage ourselves.
Couldn't agree more. Okay, so we've covered a lot of ground in our deep dive into Euclid's Elements. Maybe it's time to, zoom out a bit, recap the main points of our journey so far.
Sounds good. I'm always up for a good recap. It helps to make sure I'm actually retaining all this awesome information.
Uh-huh, I hear ya. So we started by talking about how Euclid built his entire system on these foundations of construction and deduction. We saw how his approach was really different from the modern algebra we're used to, much more grounded in the visual world of shapes.
And then we got to the mind-bending stuff. Incommensurability. Whoa, the ancient Greeks had to confront the fact that not everything could be neatly expressed as a ratio of whole numbers. It really challenged their whole worldview, right?
Totally. And to top it all off, we explored his method of exhaustion, which, foreshadowed calculus centuries before it was actually developed.
Euclid, man, he was a true pioneer. And it's inspiring to see how a work that's over 2,000 years old can still teach us so much about how to think logically and precisely.
It really goes to show that the pursuit of knowledge is a timeless endeavor. There are always new things to discover, new connections to make, even in ideas that have been around for millennia.
And who knows, maybe some of the ancient ideas we've been discussing today could hold the key to solving some of the challenges we face in the 21st century. The possibilities are endless when we keep our minds open to the wisdom of the past.
Well said. All right, folks, that about wraps up our deep dive into Euclid's Elements. We hope you've enjoyed the journey with us.
You know, it's really something else to think that a book this old can still, like, speak to us today. You know what I mean?
It's a real testament to how powerful Euclid's ideas were.
Mm-hmm.
Like the element, it's not just some museum piece. It's still relevant to how we think about math even now.
Totally. And it makes you wonder, like, what other mathematical treasures might be out there just waiting to be, dug up from the past?
Yeah, who knows what insights we might find if we took a fresh look at some of these old texts.
I mean, Euclid's work had this huge impact on, well, pretty much all of Western mathematics. So it makes you think maybe there are other traditions, maybe from other parts of the world that have something amazing to teach us.
Yeah, for sure. Like maybe those traditions hold the key to some problem we're grappling with today. It's like, history isn't just about the past. It can give us tools for the present, too.
Absolutely. And it's not just about the specific math concepts, right? It's also about how different cultures thought about problems, like their whole approach to, well, to thinking itself.
I totally agree. Expanding how we view math history, it's like expanding our own minds.
Yeah.
It could even lead to new discoveries. Who knows?
It's pretty exciting to think about. Well, I think that wraps up our deep dive into Euclid's Elements for today. It's been a real journey.
It really has. It just goes to show you human curiosity, that drive to understand things, it never really goes away.
And on that note, to all our listeners out there, we want to encourage you, keep being curious. Don't be afraid to, dig into something new, see things from a new angle. Keep asking those big questions.
Who knows? Maybe you'll be the one to uncover the next big idea, the one that's hidden for centuries, just waiting for someone to come along and rediscover it.
That's what it's all about. Thanks for joining us on this deep dive into Euclid's Elements, folks. We had a blast, and we hope you did too.